Our second pulleys video is pulleys on a horizontal surface. We're going to start with a smooth horizontal plane, and then we're going to move on to a rough one where friction comes into play. So here's this situation, and you might think that the 3 kilogram mass being less than the 5 kilogram, that there wouldn't be any motion taking place. But this 3 kilogram mass is wanting to move down, so it will pull the string into tension. So there'll be tension in this string. Consequently, there's only one horizontal force acting on that 5 kilogram mass, and that's tension. And because there's no friction, there's nothing now to stop the 5 kilogram mass from moving. In an extreme example, if this 3 kilogram mass were a mouse and the 5 kilogram mass were in fact an elephant, the mouse would still be pulling the elephant across the smooth horizontal surface. There'd be nothing the elephant could do about it. The forces acting on the 3 kilogram mass are its weight and the tension in that string, and the acceleration of the 5 kilogram mass horizontally is equal in magnitude to the acceleration of the 3 kilogram mass vertically downwards. So we apply Newton's second law to the 5 kilogram mass, and we simply have T equals 5 times acceleration. Applying exactly the same law to the 3 kilogram mass, we add the two equations together and we can obtain our value of A. So that's the acceleration in the system, and then substituting that back in to the top equation would be the easiest. The tension is 5 times the acceleration, 18.375 newtons. Now, if the surface is rough, there'll be a frictional force acting on the mass on the horizontal surface. In this case, it's the 5 kilogram mass. And for motion to take place, we require the pull force, which is the 3g weight. We require this downward force. In this case, it's 3g, but just generally, the downward force here would have to exceed the frictional force there. If it does, motion will take place. And when it does, we just set up our two equations as normal. For the 5 kilogram mass, the equation of motion would be T minus F equals 5 times A. And applying Newton's second law to the 3 kilogram mass, we would obtain that equation there. Sometimes we get asked for the forces on the pulley. There are two equal sized tensions acting on the pulley, one vertically downwards and one horizontally. The reason being, for the horizontal part of the string, there are equal and opposite tensions, one inwards from the 5 kilogram mass, one inwards from the pulley. And in the vertical section of the string, we've got two equal and opposite tensions, as we've seen, one upwards from the 3 kilogram mass, one downwards from the pulley. So the resultant force, equivalent to the two tensions acting on the pulley, because those tensions are equal, the direction will be 45 degrees, and we could use Pythagoras in order to find the resultant force. So that's the theory. I think it's time for an example. So I'll give you a moment to read that. So let's start putting our forces in the diagram. We've got a weight, 0.8 g, because B has a mass of 0.8 kilograms. There's tension in the string acting on B. There's 0.08 g, and that's a frictional force. So have a look here. It says a frictional force of 0.08 g acts on A, and there's a tension acting on A. So we can set up our two equations for Newton's second law. For A, the resultant force will be T minus 0.08 G equals mass. The mass of A was 0.4 kilograms, so it's 0.4 times A. Applying Newton's second law to B, the resultant force is 0.8 G downwards minus T upwards equals mass 0.8 kilograms times A. And when we add the two equations and divide by 1.2, we end up with A being 5.88 meters per second squared. Find the time taken for B to reach the ground. Well, initially it starts off with a speed of 0. The acceleration is 5.88. It's not 9.8 because it's the acceleration is in the system of in the pulley system. The distance travelled to the ground is 0.5 meters, and we just need to find the time t. And we can use Suvat equations because this acceleration here is constant. So using s equals ut plus a half at squared, substitute those values in, and we end up with 0.412 seconds to three significant figures. For part C, find the total distance travelled by A before coming to rest. Okay. So we need the speed of A at the point where B hits the floor. And that speed of which A has reached is exactly the same speed with which B hits the floor. So B set off with an initial speed of 0. Its acceleration was 5.88. The distance it was travelling was 0.5. Find V. V equals U plus AT. Substituting in the values gives us 2.42487 meters per second. That's the speed that A reaches at the point where B hits the floor. Now, we need to find the acceleration of A because we need to know how much further A will travel before coming to rest. When B hits the floor, A keeps moving, so at that point the string becomes slack. So now there's no tension pulling A along. The only force acting on A is the friction. The friction will provide a deceleration which will slow A down. So applying Newton's second law to A, once the string has become slack, that is the resultant force. It's the only force acting on object A. And so the acceleration is negative 1.96 meters per second squared. So once B hits the floor, we're looking now at that motion of A. Its initial speed, that was the speed that A had reached when B hit the floor. That's the acceleration when the tension in the string is 0. That's the acceleration or the deceleration caused by the friction acting on A. A is going to come to rest, so V will be 0. And we need to find the distance it will travel in this situation. There's our equation of motion. Substituting in our values, rearranging gives us 1.5 meters. Now note the 1.5 meters was the distance that A travels after the tension in the string is 0, after the string has become slack. But it had travelled 0.5 meters up to that point, because that 0.5 meters was the distance that B had travelled to reach the floor. So the total distance A moves is the 0.5 meters while under tension, and a further 1.5 meters when there's no tension in the system.